Hi all, myself Kartika. In our last class, we have discussed about what compiler is and what are the various applications of a compiler and what are the various phases involved in the compilation process. Compilation is not a single step, it involves a series of steps. And today we are going to see the first step. Before going into the lecture, let me tell an example. Consider that you are going to translate a text written in English language to Tamil language. I am using Google Translator. Once the text is given into the Google Translator, what the translator do? The first step is the translator will try to read all the characters in the text. After reading all the characters, it starts extracting each and every word in the text. And after extracting the words, it starts identifying what is that word, whether that word is a noun or that word is a verb or adjective or adverb or subject, anything, depending upon the grammatical rules of the English language. After identifying all those steps, the translator starts converting the words into Tamil language. So while converting also, it will consider about the grammatical rules of the Tamil language. So this is the first step. First step is nothing but reading all the characters and separating the words in the text. Similarly, in the first step of a compilation, the lexical analyzer is nothing but our first phase of a compiler. So our lexical analyzer scans the complete input stream one by one, and after scanning, it creates an output. The output is called as tokens. And today we are going to see how a lexical analyzer scans the characters and how it is generating tokens. Let us see that in detail in our lecture. Let's go on. General objective. So the general objective of today's class is to understand the procedure involved in construction of lexical analyzer, and we are going to apply that procedure for a source program and going to generate tokens. And these are the specific objectives. Role of lexical analyzer. The main task of lexical analysis is scanning the input. It scans the input from left to right and start generating tokens. That tokens is provided as an input to the next phase, that is parsing phase of the compiler. So the first phase of a compiler is lexical analysis. It is also known as scanner. Since it scans the input from left to right, it is known as scanner. While scanning, it identifies tokens one by one. Scanners are usually implemented to produce tokens only when requested by a parser. The main tasks are read the input characters one by one, to produce a sequence of tokens used by the parser for syntax analysis, and it is used as an assistant of parser. So the sequence of steps involved is represented in this diagram. First, when a source program is given as an input to the lexical analyzer, get next token. So this is a command. This command is sent from the parser to the lexical analyzer. On receiving this command, the lexical analyzer scans the source program until it finds the next token. After finding the token, it returns that token to the parser. Then that token is dealt with the parser. We will be seeing how parser works in our next unit. During the complete process of tokenization, symbol table is involved. So symbol table is used for getting the different types of identifiers, keywords and addresses, and after obtaining the token is added into the symbol table also. So during the complete tokenization process, symbol table is involved. So the major task of lexical analyzer is tokenization. Then what are the other tasks of scanner? Stripping out comments and white spaces, and it correlates error messages generated by the compiler with the source program. It keeps track of new line characters. In some compiler, it makes a copy of source program with error messages. If macro processors are used in source program, it expands macros. These are the other tasks of the scanner, nothing but our lexical analyzer. The two major processes of lexical analyzer is scanning, as told before. This is a simple process. Here, while scanning, comments, white spaces will be deleted. Then the next process is lexical analysis, and this is a complex process, and lexical analysis is majorly used for tokenization purpose. So our process of lexical analyzer is categorized into scanning and lexical analysis. Now we are going to see the difference between the lexical analysis, that is scanner, and parser. Why we have to separate these two? Why we need separate lexical analysis and separate parsing? One is simplicity. Since in lexical analysis, all the white spaces and comments are dealt and it is removed, complexity is minimized in parser. And also, since we have separated lexical analysis phase from the parsing phase, the efficiency of the compiler is improved. And also, it helps in portability of the compiler. And also, it helps to enhance the portability of the compiler. So, these are the reasons for separating lexical phase and parsing phase. During the lexical analysis phase, we are talking about tokenization. What is meant by tokenization? What actually token is? Let us see in detail about what is meant by token and how each and every token is generated by the lexical analyzer. Token is nothing but it is a pair of token name and an optional token value. We will have a token name and a value for it. All the keywords, operators, identifiers, constants, little strings, punctuation symbols such as commas and semicolons, everything denotes an identifier. Pattern is nothing but it is a description of the form that the lexemes of a token may take. What is meant by lexemes? So, pattern is nothing but it tells a description, what kind of pattern a lexeme should be. Then what is meant by a lexeme? Lexeme is nothing but it is a sequence of characters on the source program that matches the pattern for a token. See, here we are having a lexeme. Lexeme is nothing but input. When a particular input matches with a pattern, then that input becomes a token, right? So this is identified by the lexical analyzer. Hope you understand what is about lexemes, pattern and a token. While scanning the input, we may come across sequence of characters. When a particular sequence of character matches a pattern is nothing but a syntax. Then that group of characters form a token. So this is what a lexical analyzer is doing. It scans the input and check whether the scanned input matches with a pattern. If it matches, that particular scanned input is given as a token to the next phase, parser. This table gives an insight about what is meant by a token and what is meant by a lexeme. See, while we are scanning, I and F. Two inputs are there. Two input characters I and F. So this I and F matches with the pattern keyword. So this is formed as a token if. Similarly, else matches with a pattern. So it forms a token. If we come across operators like less than or equal to or not equal to or equal to, so these all matches with a pattern operator symbols. So this becomes a token. Then if we have some identifiers are nothing but the variables the user defines in a program. So if we come across some identifiers is also a pattern. So when we find the identifier, a pattern is matched and the corresponding token is formed in the name ID. A common name ID is given for all the identifiers, and this ID is followed by some values. While discussing the example, I will say in detail. Then this 3.14 or 0.5 or numeric constant. So constant is also a pattern. So the token for that constant is number. We have to specify the number as it is. So anything surrounded by double quotes, that is considered as a literal. So we have to give the name literal as a token. One token for each keyword. If there are operators, we have to specify the operators as it is, and one token for representing the identifiers, and one or more tokens for representing the constants, and tokens for each punctuation symbols such as left, right parenthesis, comma, semicolon. So we have to specify each and every punctuation symbol as a token. Okay. Hope you understand what are the different words that form a token. Once again I will tell, if a keyword is there, if an identifier is there, then we have to represent it as a separate token. If constants are there, we have to represent each and every constant as a token. If left parenthesis, right parenthesis, commas, semicolons are there, that also has to be represented as a separate token. And finally, if operators are there, we have to represent that operators also as a separate token, and the token is nothing but the operator itself. For example, if it is an equal to operator, you have to mention it as equal to. Okay. So this is how a particular source program is separated as tokens by the lexical analyzer. Attributes for tokens. When more than one lexeme match a pattern, lexical analyzer must provide additional information about the particular lexeme that matched. For example, 0 and 1. Both are what? Both are numbers and both match the pattern for token numbers. So what lexical analyzer should do means, it should provide additional information about this particular lexemes. So to avoid this confusion, for example, if I am representing the constant 0 as ID, and also if I am representing the constant 1 as ID, so both lexemes are mapped to a same token name. So there occurs confusion. So in order to avoid that, scanner is providing token name and attribute value. So token name, it influences the parsing decisions, and attribute value, it influences translation of tokens after the parse. So you always, token for identifier is represented by ID, comma, attribute value. So attribute value is nothing but, it is a pointer to the symbol table entry for that particular identifier. Then if operators, keywords and punctuations are there, we have to represent it only with the token name and no attribute value should be provided. If constants are there, we have to represent token by the number that is provided as a constant. So the token name is nothing but the number followed by a character string represent the constant. For example, if a constant 2 is given, the token is returned as number 2, right? If a constant 3.14 is given, we have to write a token for the constant as number 3.14. Okay? If an identifier A is there, we have to write this identifier like ID followed by an attribute value. Attribute value is nothing but it is a pointer to the symbol table entry. Since we don't know the current pointer, we will represent it with a number, ID 1 or ID 2, like that. Similarly, if we have another identifier like add, we represent this as ID 2. So this is how you have to write the tokens for the identifier. Now let us see an example program, and from that program how we can form tokens. E equal to MC square. So our lexical analyzer will scan from left to right. So what is the first symbol? E. So E is nothing but it is an identifier. So identifier has to be mentioned as ID followed by the pointer value, pointer to the symbol table entry. So let me say it as 1. Next we are having equal to. Equal to is what? Equal to is an operator. So how we have to mention the operator? We have to give the name as it is. So this is what? This is an assignment operator. So you have to represent token like assign operator. Next we are having M. M is what? M is an identifier. So for identifier we have to represent token as ID and 2. 2 is nothing but a symbol table entry. Then we are having star asterisk symbol. So this is what? This is a multiplication operator. So operator have to be mentioned in the name as it is. So the corresponding token is multiplication operator. Next we are having C. C is what? C is an identifier. So identifier we have to write like ID followed by the symbol table entry. Since it starts from 1 to, here I am representing it with 3. Then double asterisk. So double asterisk is nothing but it is also an operator. What operator it is? It is an exponential operator. What it means? It is equal to MC square. So double asterisk means exponential operator. So I am representing token like EXPOP. Then finally we are having 2. What is 2? 2 is a constant. So how we have to represent constant as a token? We have to write it as number followed by the constant itself. What is the constant? 2. So what type of constant it is? It is an integer constant. So we have to write like integer value 2. So this is how we have to segregate each and every character in a program as a token. Now let us see another example. So this is a sample program. From this program we are going to find out how many tokens would be formed. First statement, hash include stdio.h. This is what? This is a preprocessor directive. So preprocessor directives will be ignored. It won't be considered as a token. Next, coming to the statement int. Int is what? It is a keyword. So first token, then maximum, second token, then open bracket, third token, then again another int, fourth token, x, fifth token, comma, sixth token, another int, seventh token, y, another token, close bracket, a token, 9 tokens. So in this particular line we can form 9 tokens. Then a left open parenthesis. So this is also a token. So token number 10. Then what is this? So this is double slash. Double slash means it is a common statement. Usually comments will be ignored by the lexical analyzer. It won't be consider the comments while forming tokens. Next statement is if, I and f. If is what? It is a keyword. So this is also a token, token number 11. Then open bracket, token number 12. X, token number 13. Greater than, it is what? It is an operator, token number 14. Y is also a identifier. So this is also a token, token number 15. Closing bracket is there. This is also a token, token number 16. Then return is a keyword. So this is also a token. X is an identifier, token. Semicolon is also a token. Else is a keyword, token. Then open parenthesis, a token, 21. Return is a keyword, it is also a token. Y is an identifier, it is also a token. Semicolon is an identifier, it is also a token. And here another closed parenthesis, it is also a token. And finally, last parenthesis, it is also a token. So how many number of tokens are there? Totally 26 number of tokens are there in this program. Now let us see another program and let us find how many tokens are there in this program. Let us start one by one. Int, keyword, main, keyword, open bracket, close bracket is a token, open parenthesis is a token, again int is a token, identifier, equal to is an operator, 10 is a constant, comma, b, equal to 20, semicolon, then printf, then open bracket, then all this within double quotes, everything is considered as what? It is considered as a literal. So this is also a token, then comma, token, a, token, plus is an operator, it is also a token, b is a identifier, it is also a token, closed bracket also a token, semicolon is also a token. Then return also a token, 0 is a token, semicolon is a token, and closed parenthesis is a token. So totally 28 tokens are there in this program. I hope you understand how a lexical analyzer actually produces tokens from a given input. Now let us see, during the tokenization process, the lexical analyzer will omit something. It won't consider that to produce tokens. What it will omit? It will omit all the comments, it will omit all the white spaces, it will omit all the macros, it will omit all the preprocessor directive. Remaining everything will be considered for tokenization. Next, let us see the issues in lexical analysis. So lexical analysis is the process of producing tokens from the source program. It has the following issues. First issue, look ahead. Second, ambiguities. What does mean by look ahead? Look ahead is required to decide when one token will end and the next token will begin. The simple example which has look ahead issues are I versus if and equal to versus double equal to. Therefore, a way to describe these lexemes of each token is required. See, while scanning from left to right, if a particular statement is like this, if whether I has to be considered as a separate lexeme or it has to be considered together with F as a separate lexeme. There occurs a dilemma. So, a way is needed to resolve this ambiguities. Similarly, is double equal to is two equal signs or equal to or double equal to. And similarly, we have array 5, 4 and function 5, 4. So, both array reference syntax and function call syntax are similar. So, while forming tokens, lexical analyzer will have a ambiguity, so which has to be considered. Hence, the number of look ahead to be considered and a way to describe the lexemes of each token is also needed. The only solution for it is regular expression. So regular expression are one of the most popular way of representing the tokens. Next, ambiguities. The lexical analysis programs written with Lex concept. Lex is a separate software that helps in the process of tokenization. So it does the work of the lexical analyzer. The lexical analysis programs written with Lex accept ambiguous specifications and choose the longest match possible at each input unit. So Lex can also handle ambiguous specifications. When more than one expression matches with the current input, Lex will consider the longest match as a preference among rules which matched the same number of characters. So the rule given first is preferred. So these are the two issues involved in lexical analysis. Lexical errors. While scanning a input stream and generating tokens, lexical analyzer will come across lexical errors. That lexical errors has to be refined by the lexical analyzer. Lexical analyzer are not common, but they can be handled by the scanners. Misspelling of identifiers, keywords are considered as lexical errors. Usually, a lexical error is caused by the appearance of an illegal character, mostly at the beginning of the token. So, this lexical errors has to be handled and corrected by our lexical analyzer itself. Otherwise, it will create problems in the parsing phase. There are a lot of error recovery schemes followed by the lexical analyzer. One is panic mode recovery, local correction and global correction. Let us see in detail about these error recovery schemas. Panic mode recovery. In panic mode recovery, unmatched patterns are deleted from the remaining input until the lexical analyzer find a well-formed token at the beginning of what input is left. For instance, the string fi is encountered for the first time in a C program in the context fi a equal to f of x. A lexical analyzer cannot tell whether f is misspelled of the keyword if or an undeclared function identifier. Since fi is a valid lexeme for the token ID, the lexical analyzer will return the token ID to the parser. Local correction. So, local correction performs deletion or insertion or replacement of any number of symbols in the error detection point. For example, C of I equal to. So, here the scanner delete the first quote because it cannot legally follow the closing bracket, and the parser replaces the resulting single quote equal to by an assignment statement. So, it deletes the two quotes. Most of the errors are corrected by local correction. The effects of lexical error recovery might well create a later syntax error, and that will be handled by the parser. For example, consider this statement. For $T_night. So, the dollar terminates scanning of for. So, while scanning, dollar is at the end position for. Since no valid token begins with dollar, it is deleted. Then T_night is scanned as an identifier. So, in effect, it results in fortnight. So, this will cause a syntax error. We don't know whether it is a syntax error or not. This may cause a syntax error. Such false errors are unavoidable because our scanner has did the job correctly. Since dollar is not a valid lexeme, it removed it, and T_night is an identifier, so it formed that as an identifier. So, this may result in syntax errors. So, such false errors are unavoidable, and this syntactic errors will be rectified in the next phase, parsing phase. Lexical error handling approaches. Lexical errors can be handled by the following actions. First, deleting one character from the remaining input. Next, inserting a missing character into the remaining input. Then replacing a character by another character. Then finally transposing two adjacent characters. So these are the common lexical error handling approaches. Next, input buffering. We know that lexical analyzer is involved in scanning the inputs from left to right. So while scanning, the scanned input has to be placed in some place. For that, we are using buffering techniques. To keep track of the scanning process, two pointers are used, forward pointer and lexim begin. So this is a sample buffer. So initial configuration of input buffering. So lexical analyzer while scanning, as told before, it has two pointers, lexim begin BP and forward begin FP. Initially, both the pointer will point to the first character of input string. So FP pointer moves ahead to search for end of lexims. It moves here. So IN is not a correct lexim. Then INT is what? It is a correct lexim because it matches with the pattern keyword. So finally, this lexim matches with the pattern and now it forms what? It forms a token. Next, our forward pointer moves one step. So it is a blank space. As soon as blank space is encountered, it indicates that the lexim comes to an end. After identifying a token, FP move ahead of white space, that is FP ignores the white space and move ahead. After determining the token, our lexim begin will now points the next lexim I, because the token int has been identified. So this is how the two pointers lexim begin and forward pointers. This is how the two pointers lexim begin and forward pointer is involved in finding out the tokens from an input string. So this input is usually read from the secondary storage devices. Since it is so costly to read each and every character from the secondary storage devices, we go with the concept of buffering. So in buffering, a block of data is first read into the buffer and then scanned by the lexical analyzer. Each buffer will be of size n, and n is nothing but it is a size of a disk block, usually 4096 bytes. And we involve two methods to read the characters into a buffer. One is one buffer schema and two buffer schema. We use one system command to read n characters into a buffer. One buffer scheme, here only one buffer is read to store the input string. The drawback of one buffer scheme is, if the length of the lexim is long, it crosses the buffer boundary and the buffer has to be refilled. So this will aim in overwriting the first part of the lexim. So this is a drawback of one buffer schema. For example, if this buffer reaches the end of the buffer, the next characters will be refilled from the beginning. So this is the drawback of one buffer scheme. Next we go to two buffer scheme. Here two buffers are used. First and second buffers are scanned alternatively. When end of the buffer is reached, other buffer is filled. See, this is buffer 1. If this buffer 1 reaches the end, then the next buffer 2 will be filled. When buffer 2 reaches the end of the buffer 1 will be filled. So alternatively, two buffers will be used for scanning the characters. Sentinels. In order to identify the end of the first buffer, EOF characters is placed at end of the first buffer. Similarly, in the second buffer. If first buffer reaches EOF, end of the buffer is recognized and moves to the next buffer. So EOF, that is placing the character at the end of the buffer, is called as sentinel. That is placing the character EOF at the end of the buffer is called as Sentinel, and this helps in identifying the end of the buffer. So this is a simple pseudocode explaining about the Sentinel. See, if EOF is reached, forward is at the end of the first buffer, we have to reload second buffer. Forward is equal to beginning of second buffer. Now FB moves to the second buffer. Else if forward is at end of the second buffer, if FP is here, we have to what? We have to do reloading of the first buffer. Now forward comes to beginning of the first buffer. Else EOF is within a buffer, marks the end of the input, we have to terminate the lexical analysis and we have to break off it. So this is a simple pseudocode explaining the Sentinel process. The various limitations of Sentinels is, if the forward pointer is about to move end of the first half, then the right half is filled with n new input characters. If the forward pointer is about to move the end of the right half, the left half is filled with n new input characters. So forward pointer must travel more distance than the length of the buffer. So this is the biggest drawback of Sentinel. See, this is our buffer. Here we are having an EOF and here we have an EOF. So this is buffer 1, this is buffer 2. So when the forward pointer is at the end of the first half, the right half will be filled. Similarly, if the forward pointer is at the end of the right half, the left half will be filled. So forward pointer have to move once again to what? Move once again to the left half to start scanning the characters. So forward pointer must travel more distance than the length of the buffer. So this is the biggest limitation of Sentinels. Okay guys, in today's lecture, you have seen about how a lexical analyzer helps in generating the tokens, and that tokens is needed for the next phase of the compilation. We will see with another interesting topic in next lecture. Thank you all. Bye-bye.